Okay, so let's just get started with trigonometry. So, have you guys done trig at all in school yet? Um, I'm trying to annotate. Triangles. Right, so trig is um, at its core about triangles. So it looks like you guys have some experience with it. So right now we'll just go over a few basic definitions. Um, so let's say we have this right triangle here. And we have this angle theta here. Okay, so we'll call the opposite side O, the hypotenuse H, and the adjacent side A. So the side that's adjacent to theta has length A, basically. Okay, so the sine of theta will be the opposite side over the hypotenuse. For cosine, the cosine of theta will be the adjacent side over the hypotenuse. And then the tangent of theta will be the opposite side over the adjacent side. So because of this, sometimes you see people with the abbreviation SOHCAHTOA. And this is just a simple way to memorize or remember all of these different relationships. Let's see what else I have to go through. Okay, so there's more. So the cosecant, or CSC for short, that will be 1 over sine theta. So it's the reciprocal of sine. And then the secant will be the reciprocal of, it's going to be a theta here. The secant will be the reciprocal of cosine. And finally, we also have the cotangent, or COT for short, and that is the reciprocal of tangent. Okay, and we also have inverse trigonometric functions. And for these, let's say that we have sine x equals y. Then we say that x will equal sine inverse of y with a -1 here. And we can also call it the arcsine of y. Okay, so these are all the basic definitions for trig that we'll use today. Any questions? The important ones to remember are probably these three, just sine, cosine, and tangent. Those are the main functions that we'll be dealing with. Okay, so first let's talk about graphing trigonometric functions. So first we'll actually talk about a different kind of measure of angles called radians. So has anyone encountered radians before? I guess maybe not. Um, okay, so we'll talk about radians first. 1 radian is equal to 180 over pi degrees. So that means that pi radians equals 180 degrees, and a full circle or a full revolution will be 2 pi radians. So if you have this circle, just half of the circle here will be pi radians, but then the entire thing will be 2 pi radians. Okay, so when we think about the sine, cosine, tangent, it doesn't seem like they can take on negative values, right? Because previously we were only looking at right triangles, and obviously the sides are positive values. However, if we just think about the functions, we can get some negative values for the sine, cosine, and tangent functions. So let's imagine that we're on this circle in the coordinate plane. So say this is the x direction and this is the y direction. So let's say we have a point P1 at 3, 4. P2 is at -4, -3. And P3 is at 3, -4. Um, well, there might be an error in the caption, but so in the positive x direction, we take the positive values of the coordinates. So you might see that sine theta 1 equals the opposite, which will be 4 over the hypotenuse 5. However, when x is, in the negative direction for y, um, we have -4. So let's just say that this side length is -4 since it's in the negative direction. So in that case, sine of theta 2 will equal -4 over 5. Or -3 over 5, sorry. And then for sine theta sub 3, again, this is in the negative direction, so this side will have length -4. So when we do opposite over the hypotenuse, we do -4 over 5. And in that case, the value of the sine function will be negative. So what actually happens when we graph these two functions? So we have this graph here of sine and cosine. So sine is seems like this might have been reversed. Sine is in red and cosine is in blue. Um, so let's take a look at sine first. First, it starts at 0, and then it reaches 1 at pi over 2, and then goes back down to 0 at pi, and then it goes below the x-axis from pi to 2 pi. For cosine, it starts at 1 when x equals 0, and it goes down to 0 at pi over 2 and -1 at pi. So when we think about it on the unit circle, when x is 0, that would be this point here. And that has a coordinate of 1, 0. So the y coordinate would be 0 over the hypotenuse, giving us a 0 sign. And then 1 over the hypotenuse would give us 1 for the cosine function. So a few things to keep in mind for these two graphs. Notice how they actually repeat over the interval of 2 pi. So every 2 pi, the sine function will make the same shape again. So here it makes the shape, and then after 2 pi, it makes the same shape again. And for cosine, it's also repeating. It's also periodic. And the period over which they repeat, or like the number of like the smallest interval that the function repeats, we call it the period. And for both of them, it will be 2 pi. And also you might notice that the two functions are basically the same, except sine of x is the cosine function shifted to the right by pi over 2 units. So just keep that in mind because it will come in use later. Then we can also talk about some of the points where the two graphs intersect. So here are some of the intersection points. And notice that these also occur periodically. And this will only happen when we have a 45, 45, 90 isosceles right triangle. So at pi over 4, this one is 5 pi over 4. This is -3 pi over 4. And -7 pi over 4. Because when you look at a 45-degree angle, the both legs will have the same value. So cosine and sine will have the same value. And in general, that means that the graphs will intersect at all points that satisfy this coordinate here, and where k is a positive integer. Okay, and then finally, let's talk about the symmetry. So cosine x is symmetric about the y-axis. So if you rotate it, if you flip it around the y-axis, it will still be the same. There won't be any change. And that will be something important that we use when we go to the next section. Okay, and then we'll take a look at the tangent function now. So in this one, um, again, it's periodic. So the same shape will repeat every pi units. So that means that the period of the tangent function will be pi. Okay, and then another thing to notice is that the graph has asymptotes. And these are lines where the red lines in the diagram here, and those are where the graph extends to infinity or negative infinity. So let's take a look at the one here at pi over 2. Um, so as we approach pi over 2 going in this direction, the graph keeps increasing until it approaches infinity. And you can think about it on the unit circle once again, because as x gets closer to being a 90-degree angle, the sine or the y coordinate gets closer to 0. So if that's the case, as the denominator of the fraction gets closer to 0, um, and the numerator gets closer to 1, this will eventually approach infinity. And then same for the other direction. In this way, it's the same thing except we're on the opposite side of the x-axis. So these asymptotes will repeat periodically um, for all x equals 2k plus 1 over pi times pi over 2. So basically all of the um, pi over 2 times all of the odd numbers, where k is a positive. K is an integer. Okay, and then we'll also just briefly take a look at the inverse trigonometric functions. So probably the most important thing to keep in mind is the domains and ranges. So sine inverse of x has domain -1 to -1, and range negative pi over 2 over pi over 2. The cosine inverse of negative x also has domain -1 to 1, but its range will be different. Instead, it will be instead of like sine, it will be 0 to, it should be all be brackets, 0 to pi. And then the tangent inverse, it's defined over all real numbers. So from negative infinity to infinity. And its range will also be from negative pi over 2 to pi over 2. Right, so just keep in mind that sine and cosine only accept arguments from -1 to 1, and they will only produce outputs from within these two ranges. And then just for completeness, we'll also show the cosecant, the secant, and the cotangent graphs. And these are also going to be periodic. We're not going to talk too much about them. Okay, and then the final thing we'll talk about is plotting transformations of trigonometric functions. And we'll only elaborate on the sine function, since most of the other trig functions are going to have the same properties when we transform them. So let's take a look at this function here. First, we'll talk about the amplitude, which is the height of each peak from the x-axis. So if we have this sine function here, the distance marked by this line will be the amplitude. And the period is the distance between peaks. We already talked about this, but that would be like the distance from this point to that point. That would be the period. The frequency is how often the function repeats. Oops. So this is usually in terms of time, and that's why here it's defined as units of cycles per unit of time, where like the number of cycles it makes per a specific unit of time. Right, and just for like a real life example, hertz is a unit of frequency per second. So if you um, ever tuned a musical instrument, you might have tuned it to an A of 440 hertz. And that just means 440 oscillations or 440 cycles per second of the sound wave. Okay, so now let's first talk about the amplitude. So we have a few different sine graphs here. And notice how we're changing the amplitude on each one. So the blue one has amplitude of 1. The red one is 2. Most we have 3 and 4. So notice how the greater we make a, the more stretched out the function will be. So if we increase a, the function will be more vertically stretched. If we decrease it, it will be less vertically stretched or compressed. Okay, and then we can also modify the period. So in this one, we're modifying b. Let's see, here we have b equals 1, b equals 2, b equals 3, and b equals 4. So let's start with blue. It definitely has the greatest period out of all of the functions here. If we move on to red, you can see that the period starts to decrease. So it makes more cycles more often. Then with green, the period decreases even more. And with light blue, the period is the least out of everything. So that basically means that increasing b will decrease the period, which corresponds to a horizontal shrink or like a horizontal compression. And like vice versa, we also have decreasing b increases the period, or it horizontally stretches the graph. And we can conclude that the period will be determined by 2 pi over b. So the period of any trigonometric graph will be 2 pi over b. Okay, and the final thing we'll talk about is what's happening here. Oh, C. Oh, there's one more actually. Okay, so for C, notice how we're adding 1 in this one, 2 for red, 3 for green, and 4 for blue. Okay, now increasing C will shift the graph more to the left. So if we increase C, we will shift the graph to the left. If we decrease C, or in other words, make it negative, that will shift the graph to the right. And throughout everything, the period and the amplitude were both unchanged. So the only thing C changes is the phase shift, or like how shifted the graph will be. And the phase shift will be C over A leftwards. And if it's negative, that means it will be going in the right direction instead. And finally, we'll talk about D. So we're all adding different D's in this one. So 1, 2, 3, 4. And as you can see, each one is a different amount off of the axes. So that means that increasing D will shift the graph upward and decreasing it will shift the graph downwards. So simply put, D is just representing the vertical shift, or how much we shift the function vertically. Okay, so any questions about graphs before we move on to some identities? Okay, then we'll move on to ocean waves, says Richard. Thank you. Some simple trigonometric identities. So the most fundamental one, or maybe the most basic one, is sine squared of theta plus cosine squared theta equals 1. So let's try to prove this real quick. Let's bring up the right triangle again with theta, adjacent, opposite, hypotenuse. Okay, we'll start with the Pythagorean theorem. So that would be O squared plus A squared equals H squared. Now, if we divide everything by H squared, what we get is O over H plus A over H. These two are squared equals 1. And remember that O over H and A over H are equal to sine of theta and cosine of theta, respectively. Okay, so that's how we can prove this identity. And the way we get these two is by dividing both sides by either sine squared or by cosine squared. So if we divide by sine squared, we get this one. If we divide by cosine squared, we're going to get this one, I think. Yeah. Okay, and then we also have these two. So these are talking about the even or odds of the functions. So if we plug in negative theta into sine, we get negative sine theta. That means it's an odd function. For cosine, if we plug in negative theta, we just get cosine theta back, which means it's even. And these are just odd and even are just words that describe the behavior of functions when we plug in the negative of the argument. And the way we can think about it is going back to the graphs. So for sine, it's something like this, right? Where it starts at 0 at the origin. If we plug in negative theta, or that means we just flip it around. So what would happen is something like this. Notice if we also just flip the function over the x-axis, so like if you do something like that, it will also turn into this. So that's why sine negative theta will equal negative sine theta. Now for cosine, remember that we talked about how it was symmetric across the y-axis. And that basically means that if we flip it again with plugging in negative theta, it will just be the same function. Right, thanks, Richard. Okay, so now let's talk about the addition and subtraction identities for sine and cosine. Um, let's see. So first we'll go over a complex number proof using some of the things from the complex numbers handout. So if you remember, you can write e to the alpha plus theta I as cosine alpha plus theta plus I sine alpha plus theta. Right? Because e to the theta I equals cosine sine CIS theta. So the other thing is that e to the alpha plus beta I, that's also the same as e to the alpha I plus, not plus, times e to the beta I equals uh, cosine alpha plus I sine alpha times, sorry, running out of space here, sine, no, not, cosine beta plus I sine beta. And if we multiply these two out, we will get cosine alpha cosine beta minus sine alpha sine beta. So basically the cosine one plus I sine alpha cosine beta plus sine beta cosine alpha, or the sine identity. And since we have cosine alpha plus beta here and I sine alpha plus beta here, that will prove the identity. I'm kind of running out of room here. Okay, we'll do the, let's see, copy this. That's not it. Okay. Yeah, let me redraw this diagram real quick because we're going to do a geometric proof of the identities as well. So we've got sorry, just give me a moment. Okay, so we'll try to prove these two identities using this figure right here. So the first thing to notice is that um, we have a bunch of right angles everywhere. So let's just go for it. Sine alpha plus beta. Since the hypotenuse is 1, we can just look at the opposite side, which is just DE plus AE. Okay, and then we do something kind of sneaky where we do DE equals to DE over OB times OB. So just this multiplies out to DE, but as you'll see in a moment, this is pretty useful for us. And then for AE, we do the same thing but with AB. So now, if you look closely, DE over OB is actually sine of alpha. And then times OB is just cosine of beta. And then for the other one, AE over AB that's just the same as sine of beta. And AB is the same as cosine of beta, cosine of alpha. So using this diagram right here, we've been able to prove the addition identity. Okay, and then the proof for cosine will be on the handout, since we're kind of running out of room on this slide. Okay, we also have the tangent ones, and oh, this is a mistake. It should be minus here. So we can use the cosine ones and the sine ones to prove it. So cosine alpha plus beta, sine alpha plus beta. If we take these things here and plug it in here, we're going to end up with this expression. But since it's just kind of a lot of algebra, we'll just skip over it here in the presentation, and it will be in the handout if you want to check it out later. Okay, and we've also got these identities. So basically, if we shift the sine and cosine functions by certain amounts, we're going to get the different variations of what the function will be. And the way you can prove this is also by using the addition identities, just by plugging in pi over 2 or negative pi or so on for beta. And that will help you get these results. You can also take a look at the graphs and do certain transformations on them. And that will also basically give you these as well. Okay, and that brings us to the double angle identities. So first, for sine of 2 theta, the way we can prove this is once again with using the addition formula. So in that case, we would just do sine theta plus theta. And once we do everything out, it turns out we end up with this. And that's the same thing for cosine. Theta plus theta. We just use the cosine addition formula, and once we evaluate everything out, we'll end up with this. If you're wondering how we get these two, we can use the identity we talked about at the beginning. Cosine squared plus theta squared equals sine squared. Theta equals 1. And if we plug this into this one, we can come away with these two equivalent ones. And then tangent is just using these two and plugging them into tangent to get to this expression here. Let's see. Okay, and finally we have the half angle identities. So we can do this one pretty much the same way with the addition formulas. So let's say we have sine theta over 2 plus theta over 2. If we do everything out, can come away with this. Since this thing is equal to sine of theta, that will give us an expression for sine theta over 2. And the proof for that will be in the handout as well. Yeah, and if you guys want to watch videos without ads, I recommend getting AdBlock, a browser extension for it sounds like an ad. Okay, never mind. YouTube Premium. I can't do that on mobile. Just don't watch videos on mobile then. Like the watching videos on a small screen isn't great for your Yeah, that was just an ad for ad blocker. Watching videos on a small screen isn't great for your eyes. Okay, so now let's talk about these two, which are called sum, not these two, these four sum to product identities. Let's see. And you can probably guess, we also prove these using um, the addition and subtraction identities. So if you want to try that on your own, you can try that on your own time. But should pretty straightforward applications because we just plug in these values and then simplify a way to get these. So we have this checkpoint here, just for the first sine one. So I'll give you guys like a minute or so to try it on your own, and then we'll talk about it. All right, did anyone was anyone able to show it? Or were you researching AdBlock? Okay, we're gonna talk about it now. So for cosine alpha minus beta, That was cosine alpha, cosine beta, plus sine alpha, sine beta. Okay, and we want to subtract cosine alpha plus beta. So that was cosine alpha, cosine beta, minus sine alpha, sine beta. Okay, and then these two cancel, and we're just left with 2 sine alpha, sine beta. And that shows the identity. It's pretty straightforward proof. Let's see how much do we have left here. Okay, we're near the end. And then we also have the opposite. So basically what did I say for the other one? Sum to product. Okay, I guess these are product to sum. These are sum to product. And we can prove them in pretty much the same way by plugging stuff into the addition and subtraction identities. So I'll give you guys about a minute to try this one. Actually, we'll do the sine one first. So let's start with sine plus sine alpha plus sine beta. And then we can write this way, sine, this is going to be a lot to write. It's alpha plus beta plus alpha minus beta over 2 plus sine alpha, what's it going to be? Alpha plus beta 2 minus alpha minus beta over 2. Okay, and then we just take the product to sum identity, plug it in, and that will give us this expression there. So do you guys want to try this one? We'll talk about it in about a minute. All right, so was anyone able to take a shot at proving it? All right, so this is pretty much the same way as for sine. So cosine alpha plus cosine beta, we'll rewrite it as cosine alpha plus beta over 2 plus alpha minus beta over 2. The other one will be cosine alpha plus beta over 2 minus alpha minus beta over 2. And then we just plug that into one of the identities again, and we'll come away with that. Sorry for kind of skipping the algebra. Okay, and then we have these identities. So these are called the triple angle identities. And basically that's because we have triple the angle here. And yeah, they can be pretty useful at times. So let's just try to prove them in this checkpoint. And to get you guys started, what you want to do is do 3 theta equals 2 theta plus theta. And that means you can use the addition identity again. Quadruple identity? It probably is. We could probably come up with something. I mean, that's just kind of twice the sum, twice the double one, which would be 2 sine 2 theta cosine 2 theta. And you end up with something kind of messy, I guess. 2 times 2 sine theta cosine theta. I don't know what to do for this one. Cosine squared theta minus sine squared theta. I guess that's what the quadruple angle one is. I don't know if that's useful enough to memorize. Anyway, try to prove this one, and then we'll talk about it in about a minute. Okay, it's been about a minute. Was anyone able to get started with this one? Was anyone able to make any progress? Okay, so let's just do it real quick. So if we do this, we have sine 2 theta cosine theta plus sine theta cosine 2 theta. This is from the addition identities. And then we just replace the sine 2 theta with the double angle identity. That's 2 sine theta cosine squared theta plus sine theta 1 minus 2 sine squared theta. And that's the double angle for cosine. Let's see what else. Okay, and we have this cosine squared that we want to get rid of. So we come back to the Pythagorean identity. And we replace it. So we get, we solve for cosine squared theta. And that gives us 1 minus sine squared theta. Okay, now this is kind of messy, but we'll just go through it. And then if you do all the algebra out, you'll end up with the answer here. Okay, we're kind of running low on time, so we'll probably go a bit fast through all of these. So here's another useful property. If we have three angles that add up to pi, or 180 degrees, then we can change the sum of the tangents to their products, and they will be equal. We'll quickly go over the law of cosines. So basically, if you have a triangle ABC with side length C, B, and A, then you can find the side length of angle of side C with a squared plus b squared minus 2ab cosine C. So it's kind of like the Pythagorean theorem, except you adjust for it not being a right triangle with this term here, 2ab cosine C. And the proof for this will be in the handout. Okay, and we also have the law of sines. You'll usually see it abbreviated as LOS, or LOC for law of cosines. And in this one, basically the sine lengths and the sine of the corresponding angle in a triangle will all be proportional, and they will all equal 2 times the circumradius as well. So again, if we have this here, ABC, A over sine A, so that would be this angle, equals B over sine B, C over sine C, and so on. What else do we have? Okay, and then we can also get the area of a triangle just using trigonometric functions. So the area of ABC will be, let me just draw a triangle real quick, half AB sine C. So this is A, B, this is angle C. The area is just half times AB times the sine of C. And the proof of this is really quick, so we'll do that. So let's say we have this altitude here with H. So in that case, sine C would just be the opposite side, H over A. Then because we know the area is already half BC, half BH, we just plug that in to get half B times A sine C. Yeah, that would be the area formula. Okay, and there will be a graph of like, there will be a table of the most common angles, and there are sine and cosines in the handout. So some of these are just useful to memorize because you don't always have time in your competition to derive everything. Although personally, I don't remember a lot of them, so it's probably not essential that you memorize them, but it is going to be useful. Okay. Yeah, we might be out of time for the problem solving in trig. Kevin, do you want to start the Kahoot at like 3:08?
Yeah, sure.
Okay. Then we'll have like a 4-minute break. And you can all join the Kahoot now, which Kevin is going to host.
Oh, hello, troll.
Kevin, there's an option to like share your computer's sound in the screen share settings.
I selected. I should be screen sharing right now.
If you want to turn on the sound.
Wait. Oh, I see. There we go. Hey. This should be a fun, by the way. Let's see what. Do we really only have 4 people? It should be more.
I think we're missing 3 people.
Yeah. Okay, looks like most of you got the correct answer, and I'm sorry, Richard, but hard to post